Practice homework 7.2, question 1. Find the Fourier transform of signal in this figure by three different methods. A is by direct integration, by the definition. Second method using pair 17 in the table 4.1 and the time shifting property. C, third method using the time differentiation and time shifting properties, along with the fact that the pair dirt function is 1. Okay, let's finish one by one. First one is just directly the definition of the integral. So we just capital F omega is integral from the negative infinite to infinite ft times e to minus j omega t dt. And based on the figure, so we can derivation the integral from minus t to 0 e to j omega t dt plus 0 to t minus e to j omega t dt. So we just integral get 2 over j omega times e minus cosine omega capital T. So the final answer is g4 times sine square omega t over 2. For the second method is based on the so first let's write the ft function, which is rectangular function, two rectangular function, t minus t capital T over 2 plus minus, because for this is negative, so it's negative under t minus t over 2. And for the pair 17, which is the rectangular function t over tau, its Fourier transform is tau times sinc function of the omega tau over 2. And in here, tau is equals to capital T, so we can get T over capital T times sinc function omega capital T over 2. And for the time shifting property, which is ft plus minus capital T, its Fourier transform is f omega times e plus minus j omega capital T. So we can get for each part the rectangular function, the Fourier transform is t times sinc function to omega capital T times e plus minus j omega capital T over 2. So we can get the ft rectangular t minus capital T over T minus rectangular function of t, minus t over 2. we just use this equation, we can eventually get the Fourier transform is 2gt sin function omega capital T sine 2 omega t. And then we get some derivation like 2gt omega t over 2 sinc omega t 2 and times 2 omega capital T. So for this one, we can get G4 omega sine square omega t over 2. And about the third method, let's insert blank page. For the C method, we already get first ft is two rectangular function plus together is t. Oh, here is capital T, and t minus capital T over 2, and we just directly get the derivative of ft, so it's dft dt. So we can get dirt t plus capital T minus 2 dirt t and plus dirt t minus capital T. And since dirt t, the Fourier transform is 1, and also we get ft minus capital T equal to f omega e2 plus minus j omega t. So we can get the f prime t, the Fourier transform pair is ej omega t minus 2 plus e2 minus j omega t. So this is equals to for sine square minus and 2 omega capital T. And for this is the form is the j omega times f omega. So we can get eventually the f omega equals to j omega minus times square and omega t over 2. Which eventually equals to J4 over omega sine square omega capital T over 2. So this is the the answer of this question. And about next question, we already signal F1T and F2T applied at the input of the ideal low-pass filters H1 and H2. The outputs YT and Y2 of these filters are multiplied to obtain the signal YT. So first we sketch the F1 and F2 omega in the Fourier transform. So for the A, since we already know this is rectangular function and the third function, so first according to the pair 17, right, it's a rectangular function t over tau. The Fourier transform is tau sinc function and omega tau over 2. And for the pair 2, which is third t, the Fourier transform is 1. So we can get, let's insert a blank page. Okay. Then, so we can get ft, which is 10,000 times rectangular 10,000 t, and its Fourier transform is sinc function omega over 20,000, which is what we try to get f1 omega, and and for the f2t, which is delta t, is Fourier transform 1, which is the f2 omega. So we can plot its figure, which is sinc function and 1. This is 1, and then
okay, I'll see you in the morning.
And for the so for this cross point, we can know that it is 20,000 pi and 40,000 pi, and this is minus 20,000 pi and minus 40,000 pi. And this is A. For the B, the similar process is just a different function. H1 and H2 is also rectangular function. Okay. So this is directly we just simply plot this rectangular function. So we directly for the h1 omega, it's already equals to rectangle omega over 40,000. Yeah, 40,000 pi. So it's just this, and this is minus 20,000 pi, and this is 20,000 pi. And for the h2 omega, is still also the rectangle function. It's just 20,000 pi. Okay. Rectangular function omega. Oh, sorry, it's 40,000. This is 20,000 pi. So it's narrower. This is 10,000 pi. Negative 10,000 pi. This is 10,000 pi. And for the C, based on the definition, we know just simply get the in the time domain, it's integral, the convolution of the ft and ht, right? And in the Fourier transform, it's just simply multiply, which is f1 omega directly times h1 omega, and y2 is f2 omega times h2 omega, which means it's just for the first one is sinc function omega over 20,000 times rectangular function 40,000 pi omega, and for the next one is 1 times rectangular function 20,000 pi omega over 20,000 pi. So this is second times. And so we can see actually this is kind of like a filter function. It's a sinc function, and they use the rectangular function to filter this one. So for the y1 is sinc function, right? And sinc function (20,000 pi) (1 omega), which means 2,000. So sinc function, okay, so it's still filter this out. So eventually is only left is this part. This is y1 omega. And for this is 2,000 pi, 20,000 pi, and this is negative 20,000 pi. And for this part, it's no changing. It's just still the this part. So which is negative 10,000 pi and positive 10,000 pi. This is y2 omega. And for the next questions, for the question D, find the bandwidth of these three. Okay, that page. For the bandwidth, the definition is just the maximum bandwidth of 1 omega, which is the maximum of the angular frequency minus minimum value of the angular frequency over 2 pi, because we try to get the hertz, so it's gonna be, this is 2 pi f for the omega. So this is 20,000 pi over, this is 0, this maximum value, this large maximum value is 20,000 pi, so it's 20,000 pi, and over 2 pi, so it's 10,000 hertz. And for the bandwidth of y2 omega is similar. The maximum value is 10,000 and the minimum value is 0, so it's over 2 pi, so it's 2000 hertz. And for the yt, which is equals to y1t times y2t. Why? Because in here it's a multiply of this two yt, and which is let's see, user convolution property and ways of conclusion to determine the bandwidth. Okay. So for the f1t to f2t, its inverse Fourier transform is 1 over 2 pi, is 1 omega, 1 2 omega, f2 omega. So y omega is y1 omega, the convolution of 1 2 omega. So from the Weiss property of convolution, it follows that the bandwidth of y omega is the sum of the bandwidth y1 and y2 omega. So y omega it should be the bandwidth of y should be the bandwidth of y1 omega plus the bandwidth of y2 omega, which means it's just plus them together. 10,000 plus 5,000, so it's 15,000 hertz, which is a bandwidth of y omega.